All right, our next speaker is Jihyeok. Sorry for my pronunciation. And the title of the paper is Feature-Sensitive Coverage for Conformance Testing of Programming Language Implementations. Now the stage is yours.
Yeah, thanks for kind introduction. So I'm Jihyeok from Korea University, and this work was collaborated with KAIST. So in this talk, I will first explain the background of this work and then introduce our new coverage criteria called feature-sensitive coverage. So let's consider a programming language L1, and each language specification describes its syntax and semantics, and there might be many different implementations exist, such as compilers, interpreters, and so on, and all of them must conform to the specification. And we can check this conformance using conformance tests, and each of them consists of a program and assertions that describes what is the correct behavior of the program according to the semantics described in the spec. And how can we measure the quality of conformance tests? There might be multiple different ways. One possible way is to utilize coverage information in the implementation, but it is not that good option because, as you know, there are multiple different implementations. So it means that it is not a uniform metric, and it is highly dependent on implementation. But if we use coverage information in language specification, we can get a uniform quality metric because there is only one language specification. For this approach, first we should extract some mechanized specification from the specification and then build a control flow graph, and then should measure some graph coverage in the CFG using the conformance test. And it represents the quality. And also we utilize this coverage information in other applications such as coverage guided fuzzing or test minimization. And this coverage information is parameterized with coverage criteria. And each criterion is defined with its own test requirement. For example, another coverage criterion is defined with nodes as test requirement. It means that it only considers nodes, which nodes are covered or not by conformance test. But there are many different coverage criteria presented by other researchers, but we realized that they are not enough for this approach. So I will explain why. So I will use JavaScript as the target language, and this language is a dynamically typed language with complex semantics, so it is a good target because we need to check this conformance of JavaScript implementations. And also it is not easy to understand even simple addition or subtraction operations. For example, we can, in the traditional way, we can add some numbers like this, or we can add even different types of values like this, object with numbers, or it sometimes returns string values rather than number values. And sometimes it throws a runtime type error in certain conditions. And I will use these examples to explain why existing coverage criteria are not enough for this problem. In this motivating example, the program P1 adds a number value 1 and big integer 2, and it throws type error. Why? We need to read the specification. This is the JavaScript language specification, and it consists of many abstract algorithms, pseudocode style, and it describes the semantics of each language feature. For example, this algorithm describes the semantics of addition operation, and it utilizes another algorithm as a helper function, and also it utilizes another one like this. And in this algorithm, in step 5, after complex process, it checks the types of left and right side values. If they are different, it throws a type error. So this is why this program P1 throws a type error. And let's consider the control flow graph in this language specification. And let's say that this line is a node 1. And if we measure node coverage, it means that test requirements are nodes. And we can say that the program P1 covers node 1. And now let's consider another program, similar one, but now we utilizes subtraction rather than addition. So it also draws type error because of the same reason. This algorithm describes the semantics of subtraction now, and it also utilizes the exactly same algorithm as a helper function to describe the similar semantics. So we can say that also program P2 covers node 1. However, it means that they cover same TRs. It means that we cannot distinguish them only by using this coverage information. In other words, if we use this node coverage information in coverage guided fuzzing, then in this process, the program pools are managed by coverage information. But these two programs have exactly same equal coverage information. One of them will be removed from the program pool. So, but actually, these two programs represent different edge cases. P1 represents the edge cases of the addition operation, and the program P2 represents the edge case in the subtraction operation. So it is much better to keep both programs in the program pool. So to do this, we represent feature-sensitive coverage criteria. So feature-sensitive coverage criteria, it divides the TRs with the innermost enclosing language features. I will explain the example. So in this example, there are two different language features, add and sub. And if we measure the feature-sensitive node coverage, now the test requirement becomes a pair of feature and node. Now the program P1 covers add 1 because it covers node 1, and at this point, the innermost enclosing feature is add. Similarly, the program P2 covers the sub 1, but it is different with add 1. It means that now we can successfully distinguish the programs P1 and P2 with feature-sensitive coverage criteria. And also we can apply k-limiting approach to this, for example, like this. So it means that we track not only a single feature, but at most the k features in the test requirement. So if we measure two feature-sensitive node coverage for the program P3, now P3 also covers node 1, but the innermost enclosing feature is add, and the next innermost one is sub. So this program P3 covers this TR. But so I introduced the core idea of feature-sensitive coverage criteria, but they still have a limitation. So I will explain this limitation with the second motivating example. So in this second motivating example, the program PR now adds a symbol value with a number value 1. It also draws type error, but because of the different reason. So I will explain why in this specification. So in the specification, it follows similar execution paths like this, but actually in this algorithm, in step 3, it tries to convert the left side value into a numeric value like this, and actually into a number value like this. So, so using the two-number algorithm. In the step 6, it checks the type, and if the type is symbol, it draws type error. So this is why the program P4 draws a type error exception. Now let's say that this line is node 2. Then if we measure the one feature-sensitive node coverage, now the program P4 covers add 2. Now let's consider another program, similar but different order. Now one adds a symbol. In this program, in this pack, the step 3 will be successfully passed, but in step 4, it tries to convert now the right side value into a number using two-number algorithm. It also draws type error because of the same reason. So it also covers add 2. But actually they are equal. It means that still we cannot distinguish these programs, but they have different information representation. So program P4 represents the edge case in the left side value, about the left side values of addition operation, but program P5 represents the right side values of the program of addition operation. So it is also better to distinguish them To do this, we utilize the call path information starting from the language feature. So not entire code stack, but call path is starting from the language feature. So we say that it is a K-feature call path sensitive coverage. So now if we measure the one FCPS node coverage, now the TR is a triple feature, call path, and node. And we know that feature and node is add and 2, but we also consider call path is starting from the add. So 3, 4, 5, 7. So this program P4 covers this TR. Similarly, program P5 covers has this call path, but slightly different with the above one because of these nodes. The call nodes 5, 6 represent the step 3 and 4 about the conversion of the left and right side values respectively. So now the program P5 covers different TR. It means that we can successfully distinguish P4 and P5 if we use FCPS coverage. So these are a high-level idea of our new coverage criteria. To evaluate our approach, we implemented a tool named JEST-FS. I'm sorry. Yes, I'm sorry. So in the previous work, we presented a tool named JEST, which is a JavaScript conformance test generator using coverage-guided fuzzing. At the time, we only utilized node and branch coverage information, but now we extended our tool JEST with our new coverage criteria, KFS and KFCPS coverage criteria. And we executed our tool in 50 hours with 5 different options. And our target JavaScript spec was the latest one at the time. And the target JavaScript implementations were 4 engines and 4 transpiler heavily used in the development process. So first, we evaluated the conformance bug detection ability of our tool. So as a result, our tool successfully detected, 42 engine bugs and 101 transpiler bugs. And after reporting all of them, 85 bugs are officially confirmed by developers, and 83 bugs are newly detected bugs. Now also, we evaluated effectiveness of K feature-sensitive coverage criteria. After applying the basic feature-sensitive approach, we can detect 28 more conformance bugs, and this program represents this situation. So this program only can synthesize it with at least one feature-sensitive coverage, and the expected result is normally termination, but Babel cannot compile this program and throws some crashes. And after applying 2 FS coverage, we can detect 90 more conformance bugs like this, and this program represents this situation. So this program only can be synthesized with at least 2 feature-sensitive coverage, and the expected result is just string value of f. But in JavaScript core used in Safari, the result is the string value async. Finally, we also evaluated the effectiveness of feature call path coverage criteria. After applying call path extensions, we can detect 4 and 9 more conformance bugs. And this program only can be synthesized with feature call path extensions. So the expected result is range error, but in Gride.js, this program normally terminates without any exception. To conclude, we presented a new coverage criteria called feature-sensitive coverage criteria with and their variant for conformance testing of PL implementations. And to evaluate our approach, we implemented the JEST-FS and experimentally showed the effectiveness of our approach by detecting more conformance bugs in real-world JavaScript implementations. So this is the end of my talk. Thank you. Thanks for listening.
Just a reminder that there's a microphone in the middle of the room. If you have questions, you can walk here and line up. So, yeah.
Hello, thank you for the talk. I am Youn from KAIST. I have two questions. First one is, can you show me the slide number 5 again, please?
Hey, number
5.
5.
Yeah.
This one?
Yes. Here, I quite didn't understand why traditional coverage metrics can't differentiate those two, because it seems like they cover two different functions.
Yeah, actually, so I skipped the detailed explanation. So I assume that already the other parts are already covered by other programs. So we only focus on the type error case node here. So it covers by two different programs. So one of the program will be removed from the program pool.
Okay,
Yeah.
so regarding the code coverage, there's nothing new in this example, right?
Yeah.
Okay.
Exactly.
And the second question is that for the evaluation, it seems like you used only 2 for the maximum K.
Sorry?
You used 1 or 2 for the K value.
Yeah.
Yeah. Have you tried any bigger Ks for the evaluation?
Yeah, so with bigger K, we have some explosion problem because it increases the number of test requirements. So here, it describes the TRs, the number of test requirements in the table, node, and branch. So it increases the number of test requirements. If we use the more than or equal to the 3K, then there are really many test requirements. We cannot cover many parts in the 3 FS coverage. Yeah.
So empirically, 3 would be the starting point where it explodes.
Sorry.
So under your observation, 3 is the point where it starts to explode.
Yeah.
Okay.
We think that. Yeah.
I see. Thank you.
Hi, Jackson Mayo from Sandia. One of the most famous and powerful testers for language implementations is the C-Smith fuzzer for C compilers. Could your approach be used to measure the coverage achieved by C-Smith and help understand its effectiveness?
So it means that your question, is it possible to apply this approach to C?
Yeah, and specifically there are existing fuzzers like C-Smith to evaluate C compiler conformance.
Yeah, so I think it is possible to apply this approach, but actually we need some coverage information in the language specification. So JavaScript actually have good language specification, so we can utilize that coverage information. But in C, I think there is not yet coverage information from the specification. So
there are formally verified compilers like CompCert, so you might be able to leverage that for the specification.
Yeah, so if we can use that information, then I think it is possible to use our approach for that C compilers, fuzzing, yeah.
Thank you.
Yeah.
Any other questions? All right, then let's thank our speaker again. Thank you.
Thank you.